Okay? Let's try to remember where we are, because we're going to go forward from here. Right? We've been doing null hypothesis testing. Right? In null hypothesis testing, so the question is are our results due to chance, or is it due to some manipulation or some pre-existing group, something that's different about what we're looking at, right? That's our basic question in null hypothesis testing. Now, in order to do the hypothesis test, we set up a null hypothesis, a hypothesis of no difference. We're going to be setting up another one today, and I'll show you when we get to it. We're going to do other examples, but we're not there yet. And what we did, like with the kids who lived near power stations, right, we found their mean. And then what did we do with their mean? This is just recapping what we've done so you remember what we're doing. Right? We found the mean of kids who lived near power stations. What did we do with it? I found the mean. It was 103.48 for the kids who live near power stations. What did I do with it then? In order to do a hypothesis test. Did I just go and say, oh, 103.48, that's higher than 100. These kids must be smarter. I made it into a z-score. What kind of z-score did I make it into? Was it a z-score based on individual scores? Essentially, think, what was in the denominator? What was in the denominator of that z-score? Yeah, the standard error, right? Because it was about a mean. Why did I turn it into a z-score? Why did I care about turning it into a z-score? What was I ultimately looking for? Yeah. Mean or higher. Yeah, right? I was interested in the probability of a group mean of 103.48 or higher. Okay? And I found the probability for it. What was that probability called? The p-level. The p-level, right? How did I make my decision about whether that group score, right, that mean, whether it was extreme enough to warrant saying that it was due to power stations? Yeah, what did I do? I compared it to an alpha level. Right? I compared it to an alpha level to find out. Now, what was my rule? Comparing my p-level to my alpha level, what was the rule? What made the decision for me? If my p-level was what? Higher or smaller? Greater or smaller than my alpha level? Smaller, right? If my p-level was smaller than my alpha, then what happens? What's the result then? Yeah. Yeah, we reject the null hypothesis and we say that our results are statistically significant. Yeah.
You said that alpha was like 0.05 or 0.01.
Yeah.
So if your like the p-level is 0.03,
Yeah.
would that still be less?
Okay, so here's her question. She said, you said that the alpha could be 0.05 or 0.01. What happens if you get a p-level of 0.03? Alpha needs to be decided before you look at your results. Okay? So in theory, if you chose 0.01 and you got a p-level of 0.03, in theory, you couldn't find significance. In practice, people probably would consider it significant. How do you choose which alpha? Actually, that speaks to what we're going to talk about today. Okay? So let's save that for a minute. If I don't answer it, like bring it back. Okay? Yeah?
Did you say that when you rejected all hypotheses, you had a possibility of results were statistically significant or insignificant?
Say again, if we reject the null hypothesis, then what?
Are your results statistically insignificant?
No, significant. Significant. Significant in this case means you've rejected the null. You're saying that your group is different from whatever you hypothesized, your null hypothesis. And the null hypothesis was a hypothesis of no difference. Okay? So everybody like, and the other thing was, so we compared our p-level to alpha. What was the other way of doing it? There's a different way of doing it. We could compare our areas under the curve, our probabilities. What else can I compare for significance, to determine significance? This warrants a picture, I believe. right? Like, if this was my alpha level, so I compared my p level, those are areas under the curve. What's the other thing I was able to compare for significance? There's area under the curve. What corresponds to the area under the curve? How about axis values, right? Values along that axis, okay? Anybody remember? What was this called? It would be a z-score that we get from the table based on my area under the curve, based on that alpha. What was that called? I believe we did it. I'm hoping we did it. Does the term critical value mean anything to you? It doesn't. Oh, okay, good. Then it's not that you've just forgotten everything. Good. I wasn't sure. It was like the middle of my page. Okay. So let's talk about that for a minute, and then we'll pick up where we were going. All right? I can compare. You'll understand how I can compare my p level to my alpha, right? But I can also find out the z value. The z value. Now there's the z that corresponds to this area under the curve. And there's the z that we calculated. Right? What was the z that we calculated? Anybody have their notes there? What was it? 1.16, yeah. Okay? What I could also compare is that value, and that value sometimes is called a z obtained or a z observed. It's the z you get from your data, as opposed to the z you get from your table. Okay? That would be this. So that would be a z corresponding to an area of 0.05. Now I know this because I've done this 100 times. It's 1.645. Right? It's not 1.64, it's not 1.65, it was right in the middle. So then I could compare my z value here with this. This z is called a z critical value. A z critical value. Very often, or people will call it a critical z. I usually write zCV. So you should know where that comes from. So if I compare that, right? So I have my 1.16 is going to fall, I don't know, let's say here. So then you can compare your z-scores as well. Yeah. From the table. Yeah, right? My alpha is 0.05, so that's the 0.05 is the area under the curve. What column is that going to show up in? On your z table, what column does that show up in? The beyond z column. And then I look over, and the z that corresponds to that is 1.645. Okay? So I could compare these two, and because it falls here, you can think of this as a rejection region. Right? Because again, if your z gets extreme, your p-values, right, your probabilities get small. So because my z obtained falls not within the rejection region, we failed to reject, which is what we did, right? Those were our results. Yeah?
Can you just repeat how you got this z obtained? Like, I understand how to get a z-score, but how do you have two of them? Where?
Again, this was the one that I got by doing this. Right? That was that. This z is from the table. I'm still seeing consternation. Remember, we did this example in class, right? This was 103.48 minus 100 divided by whatever that standard error was. I don't know. Anybody have it? 3? Right? That was that example, the example in this chapter that we were working on. So you see where that's coming from? Okay. So then, does the other one make sense now?
I understand where you're getting 1.16 from.
Yeah.
How are you getting 1.645?
Again, the table, right? If you go to your z table.
Yeah, how do you, what are you basing it? I get that they come from the table, but what are you basing?
What do I have there? Forget the value, what do I have? What information have I given you? I've given you alpha. Alpha is a probability, and it's that area under the curve is 0.05.
Oh, you found alpha. You used the alpha value to find another z?
Right? Right. This is an area under the curve. So we work backwards to find the z-score that corresponds to that. Yeah?
So then the critical value is just the z-score times alpha?
Yeah, or you find on the table is another way of saying it. Is that good?
So there's only two different types of, there's only two different z critical values because there's only two values for alpha.
Yeah, I guess you could say that. Yeah, for z-scores. See, the reason why I don't want to say that is because for every test, we're going to do different tests, right? When we get to different tests, we're going to have to use different critical values to make this comparison. Typically, when we do z-scores, the only critical values are going to be for 0.05 and 0.01. But I don't want to lock it in so much to that, but generally, that's the case. Maybe?
Yeah.
Maybe. Okay. We're going to do another example also, which will make it clear. Other questions? Other questions? I'm hoping that, yeah?
Could you just compare the p levels if alpha is a p level, 0.05?
Well, don't call it a p level. It's a probability.
Or a probability.
Yeah.
So then you could look up the probability for finding the z-score 6.
That's what we did. That's exactly what we did.
So, okay. So are you just showing?
They're just two different ways to do it. This way is the more typical way to do it. That's why I'm showing it to you. And we'll do it in the next example that we do. But okay, so understand, in this hypothesis testing, there are just two ways that I've shown you to get the same answer. One is by comparing your p level to alpha, in which case, if your p level is smaller than alpha, you reject. The other case is comparing my z obtained from my z critical value. If the z obtained is larger or more extreme than your z critical value, you reject. Yes?
Can you say the part after the other case, sorry, the z-score obtained from the critical value?
Say that part again? Yeah. If your z obtained is more extreme, and I say more extreme instead of larger because it could be in the negative direction as well. But if your z obtained is more extreme than your z critical value, then you also reject. Because remember, right? Extreme z-scores correspond to small p-values, probabilities. That's why.
Wait, so if it's more extreme than what?
Then your z critical value, then your critical values.
Yeah. Then you reject it or
You reject. Again, look at your picture, folks. Either you're looking for a small area or a large z-score. Really get that in your heads, because that's just going to help you to extend your examples. We'll do something in class and you'll say, okay, she went here, I know that that's what it means. But then when you see another example, you should be able to generalize to it. Yeah?
So the z-score corresponding to, so the 1.16, if it was greater than 1.645,
Yes. Yes. In this case, we failed to reject. Okay? We will do another example, and we'll walk through it pretty slowly. But before we get there, we have to talk about some other stuff. Oh, by the way, this might amuse you. Okay? This is something somebody gave me. He says, can my boyfriend come along? And he says, I'm not your boyfriend. And she says, you totally are. And he says, I'm casually dating a number of people. And she says, but you spend twice as much time with me as anyone else. I'm a clear outlier. And then he says, your math is irrefutable. And she says, face it, I'm your statistically significant other. It amused me. It's a cute website, actually. Who'd have thought statistics would be amusing, huh? All right. Okay. So we have this basic idea of null hypothesis testing. That was developed by Fisher. This basic idea of how to go about testing a hypothesis. And even though he wasn't particularly tied to the 0.05 level, but we attribute it to him, But a couple of other statisticians came along and said, you know what? Fisher was too wishy-washy for us. We want to envision hypothesis testing in a stricter kind of structure. And this is how we're going to go about doing it. First of all, you have to imagine, okay, that there are two actual situations, what we might call reality, and we'll put it in air quotes, right, of the world. Actual situation is either the null hypothesis is true or it's not true. Okay, those are the two possibilities. Either it's true or it's not true. Okay? When somebody does a study, they have two possible decisions to make. Either they accept the null hypothesis or they reject it. Okay? Those two possibilities, those two situations generate 4 scenarios. So let's take a look at what those scenarios are. Let's first look at the good ones. Okay? So let's look here. In the actual situation, the null hypothesis is true, and the researcher accepts it. Right? Doesn't reject it, accepts it. That would be a correct decision. The null hypothesis was true and we kept it. Okay? The other correct decision is if the null hypothesis is false and we reject it. That's also a correct decision. But there are 2 scenarios in which we can make 2 different kinds of errors. Okay? Let's look at them. This one, the null hypothesis is true. And in this case, what do we mean by the null hypothesis being true? The null hypothesis being true would be that the kids are no different. Right? Just tying it back to the example we were doing, that the kids are no different. But if the decision is made to reject the null, then we have made what's called a type 1 error. A type 1 error. Okay? The null hypothesis is really true, but we've rejected it. All right? Now, let's go to the other type of error, and we'll keep going back to this, though. All right? The other type of error we could make is when the null hypothesis is really false, that the kids really are different, but we've accepted the null. That's called a type 2 error. The null hypothesis is really false, but we failed to reject it. We accepted it. Okay? So these 2 statisticians, Neiman and Pearson, said, the whole point of hypothesis testing really should be to quantify those errors and make them as small as possible. So let's talk about the probabilities of those errors. First of all, let's look at type 1 error. The probability of making a type 1 error is alpha. That's what alpha is. It's rejecting that null hypothesis when the truth is that it's true. Okay, so its probability is alpha. We set it. As researchers, we decide on what that's going to be. Okay? Now, what about a type 2 error? The probability of making a type 2 error is the Greek letter beta. Beta. That's its probability. We will calculate that in chapter 8. Okay? Now, the flip side of making a type 2 error is making a correct decision. That probability is 1 minus beta, and that is something called power. Power is a real important concept. That's also going to be in chapter 8. Power is the probability of rejecting the null when it should be rejected. Rejecting the null when it should be rejected. Okay? So power, you want power to be really high in any experiment. Generally, the goal of these tests is that you want alpha to be as small as possible and power to be as high as possible. Okay? Now, what are the basic questions about these types of errors? Well, first of all, how do I know if I've made a type 1 or a type 2 error? How do I know if I've made a type 1 or type 2 error? Or why would I make a type 1? Let's do that for a minute. How could I possibly make a type 1 error? I can't walk over here. I have to walk there. How can I make a type 1 error? Yeah? setting alpha too high, well, that can affect it, but it doesn't determine making the type 1 error. Any other ideas? Type 1 error, rejecting the null hypothesis when it's really true. How could that happen? No ideas? Yeah. Dealing with an extreme observation. Very good, okay? These errors are not errors that you've made because you were a lousy researcher, okay? These are not errors in the typical type of, oh, I made a mistake because I forgot to count these people, or I took a bad sample, or something like that. That's not what these errors are about, okay? A type 1 error could happen just by chance. The same thing with type 2. They could happen just by chance, right? A type 1 error, let's go back to this for a minute. Right? A type 1 error, so let's say our rejection region is over here, and I get a value that's there. So I would reject the null hypothesis, right? Okay? But it could have been an error. Why? Because it's possible if a value falls out there that all it is, it just happens to be a weird sample. It just happens to be an extreme value. For example, if I flip a coin thousands of times, there is a chance that I will still get 10 heads in a row. It may be a very, very small chance, but it could happen, right? So that could be, you could get an extreme value just by chance. That's a type 1 error. Every time you do a study, there's that possibility, okay? And a type 2 error is the same thing. You could still, it's, like I said, it's not that you've made a mistake because you're a bad researcher or something. It's just by chance you could be getting values that lead you to one decision or the other. Okay? Okay? Questions on that? Questions on that? You're not even sure which questions to ask, right? Because there were too many negatives in those sentences. Okay. When we do the examples, you'll see. You'll see. Because it's really, it's important to get that down. Here's an example, okay? I've been following what the drug companies have been doing, particularly with antidepressants over the past couple of years, because there have been major studies about what happens when adolescents are given antidepressants. Does it increase suicidal ideation? There's a variety of things that have happened over the past couple of years. And one thing that was interesting to note was that what some drug companies, what they could do, and what some of them have done is, let's say they do 10 studies on a drug. Right? 10 clinical studies on a drug. 9 of those studies show no results, right? They failed to reject the null hypothesis. They saw that there was no difference. But one of the studies showed that there was a difference. Which one got published? Yeah, but what was it likely to have been? A type 1 error. Because how do you know if you've made these errors? You only know, that's the kicker. You don't know. In general, you don't know if you've made a type 1 or a type 2 error. The only reason you know, generally, is if somebody replicates your studies. Is if somebody replicates your studies. Because then if they do it several times, you'll see if only 1 out of those 10 studies finds a difference, then it's likely that it was just an extreme sample. And it's unusual. Okay? And it wasn't a real effect. It was just an error. Which is why, by the way, in drug studies we do multiple trials. You know, for a study in cognition of undergraduate students, it's not necessarily the same deal. But for drugs, it's really important. So there's been a push, actually, for drug companies to start publishing on their websites exactly what clinical trials are being undergone. So that people know, and they can't just get away with reporting the positive results. Now, it's supposed to be a voluntary project. I don't know who's doing it. I don't know how much they've put up. But it's a step in the right direction. Okay? Now, what are the pluses and minuses? If you make a type 1 error, what's the problem with that? Right? I reject my null. I say there's a difference when there's not. What's the cost of doing that? No cost? You're happy doing it? That's right. That's right. What if that happened in a drug study? You're saying that the drug works when in fact it doesn't. And that has a lot of ramifications, right? There's the obvious clinical ramifications of prescribing medications for people that don't work. But there's all sorts of secondary ramifications, like where does the money go? Where does the money go? If you have a study that says this drug is a promising drug, the money for research goes there, right? And it usually gets taken away from somewhere else. So there's all sorts of things like that. But what about a type 2 error? What happens if you make a type 2 error? Type 2, again, is saying that there's no difference or there's no effect when in fact there is. Is there a cost of making a type 2 error? Is that a problem or not a problem? Yeah.
If you say that a drug isn't effective and it is, then you could be limiting treatment options or...
Yeah, that's right, right? If you say that a drug isn't effective, but it really is, you know, somebody could say, okay, we're going to shelve this line of research. And then something that's potentially useful gets, you know, put aside. So in the social sciences, we tend to treat type 1 errors as more serious than type 2 errors. Usually we think of it as worse to say, yes, this works, and be wrong, than to say, no, this doesn't work, and be wrong. That's not always strictly true, but in general. In general. Okay? So, Neiman and Pearson were very big on this. And by the way, it's interesting because Fisher gets credited with this stuff, even though he was not impressed with this whole little paradigm at all. Okay, so let's talk about ways to reduce type 1 or type 2 errors. Now again, alpha, your type 1 error rate, is within your control as a researcher. And you should know, if you're doing an example and there's no alpha there, use 0.05. If it doesn't say, use 0.05. So that's within my control as a researcher. Now, how do I reduce the probability of making a type 1 error? And this goes back to your question that you were asking me before, right? The probability of making a type 1 error, why don't I just always make it 0.01? Right? If type 1 errors are bad news, why don't I just always make it, and these are theoretically similar curves, why don't I just always make it 0.01? Well, look what happens, right? If this is my rejection region, yeah? So if I reduce alpha to 0.01, what am I doing to the size of my rejection region? I'm making it smaller, right? That means that if I make alpha smaller, I'm also increasing the probability of making a type 2 error. Because type 2 error is when I'm failing to reject, right? So if I make it harder to reject, I'm making it harder to reject. So if I make that alpha smaller, to make type 1 errors smaller, I'm making type 2 errors bigger. And we'll talk more about those when we get to chapter 8, but understand that trade-off there. Another thing that you could do is if you want to reduce type 2 errors, let's say I want to reduce type 2 errors. You could go from what we call a 2-tailed test to a 1-tailed test. Now, what do I mean by that? Well, the question that we've been asking, let's take a new page here. What was the question? What was the question with the power stations? Anybody remember the wording of the question? I believe the wording of the question was something like, does living near power stations increase IQ? Or something like that, right? That is what we call a directional hypothesis. You are looking in a particular direction. It's a directional hypothesis. Directional hypotheses, you'll recognize them because the words in the question are something like, did it make it higher? Did it make it bigger? Did it make it lower? Did it make it smaller? Greater? Less than? It's indicating that you're looking in a direction for your effect. So it's a directional hypothesis. That results in what we call a one-tailed test. And that's what we've done so far, only a one-tailed test, which means you put the alpha all in one side. Depending on which side you're looking for, it could be down in this side, but it's all in one side. That would be my 0.05. Okay? That would be a one-tailed test. Now, what if I ask the question differently? What if instead, does living near power stations affect IQ? Does it create a difference in IQ? Does it alter IQ? That's what we call a non-directional hypothesis. Non-directional. I have not specified a direction to look for the effect. Okay, it's a non-directional hypothesis. A non-directional hypothesis results in a two-tailed test. Two-tailed, meaning you're looking for the effect in both areas, both directions. So it would be here and here. But your alpha, you don't want your alpha to be more than 0.05, so what do? You cut it in half. So really, the area you have here is 0.025, and the area here is 0.025. Because you're not sure where the effect is. Maybe living near power stations increases IQ, maybe it lowers it. You're not sure. So you're looking in both directions. This is a two-tailed test. By the way, mostly we just do two-tailed tests, but I'll talk about that more in a minute. Let me get to the point. Okay? So the point that I was making is that if I want to reduce type 2 errors, I go from a two-tailed test to a one-tailed test. Why? Look at this. Look at this. In a one-tailed test, right, is the rejection region bigger on that one side than in the two-tailed? Yeah. I'm making the rejection area bigger. If my rejection area is bigger, that makes it easier to reject. That's a decrease in type 2 errors. So moving from a two-tailed test, instead of doing a two-tailed test but doing a one-tailed test, that lowers the probability of making type 2 errors. Okay? Now here's the problem. Here's the problem. So why doesn't everybody just do a one-tailed test? Well, there's a couple of things. One is that you often don't know the direction of your effect. You know, it's really easy to talk about, does Kaplan's increase SAT scores, or does a diet plan reduce weight, right? That's easy. But most of the stuff we study, we're not so sure which direction it's going in. So that's a problem with doing a directional hypothesis or a one-tailed test. The other one is kind of philosophical, right? Let's say you believed your results were only going to be in a particular direction, okay? So I specify a one-tailed test. I say, okay, I'm going to put all my alpha up here. I think it's going to show up there. And then you test your results, right? You get your data, you test them, and your result falls down here. You can't test that result because it's in the wrong direction. Because if you tested it for significance, let's say you were testing a depression drug, okay? And you thought it would, no, I don't like that direction. Something that increases, I don't know. Some kind of drug that increases intelligence. Let's make it up, okay? A drug, yeah, you're all like, yeah, that would be good. A drug that increases intelligence, okay? So you expect your result to fall out here somewhere, and that's how you've specified it. But lo and behold, you give these people the drug, and what does it do? It lowers their intelligence significantly, or you think it might be significant. Okay, not good, but you might want to test it to like warn people, don't use this, drug. Okay? If it falls down there, you cannot test it because you've already specified an alpha up here. If you tested it here, it would be like saying, okay, let's just put some more alpha down there, some more area, and that would be a 0.025. So you've instead taken your 0.05 alpha, that error rate that you're willing to tolerate, and you've increased it to 0.075 because you looked at the results. Like there's this old joke about a guy who's practicing shooting. So he's shooting at the side of a barn, and he sees where his bullet shots are clustered, and he goes over and he draws the bullseye around it, right? Because you've seen the results. You've seen the results, so then you're playing with things after the fact. That's a problem when you've already seen where your results are located. Yeah?
I mean, if there isn't an agenda, wouldn't it make sense to do that?
If there isn't an agenda. Well, you still have, again, you're changing the probabilities because you've already seen the results. So ethically, you're not allowed to do that. Technically, ethically, you're really not supposed to do that. Do people do that? I'm sure people do that. Okay? But, and then they may come up with other reasons why they're doing it. But you're not supposed to do that. So this is what happens. The question is, doing a one-tailed test versus a two-tailed test. You will get some people that say, you never, ever, ever, ever do a one-tailed test because they're afraid you're going to do this. All right? But then I've had classes where I have students from other disciplines look at me and say, no, we always do a one-tailed test because your research is useless unless you can specify a direction. Okay. Different disciplines do different things. There's two things you need to do. For those of you who are doing any research at all whatsoever, find out what your discipline does and then report it, right? When you're reporting your results, you have to report whether you're doing things as a one-tailed test or a two-tailed test. Then people know. But you might get flack. If you do a one-tailed test, you seriously might get flack from people. All right? Different journals may not publish it. They might not think it's worthwhile. So just to let you know, we tend to be, so the expression we use is conservative. We tend to be conservative and generally do two-tailed tests. Generally do two-tailed tests. It doesn't mean that a one-tailed test is necessarily wrong, but you might get flack for it. Okay? All right, questions on that? Let's do an example. How far can we move that so we can see what we're supposed to see? Huh. All right. For the past semester, a high school psychology teacher tutored 9 students in preparation for an AP psychology test. According to national data, the AP scores are normally distributed with a mean of 40 and a standard deviation of 5. The mean performance of the 9 students is 44. Is the mean of tutored students different from the mean of the population of students who take the AP test who aren't tutored? That is, do they constitute a different population? Okay? So here's the question, right? I want to know if tutoring will increase AP scores, essentially. That's what I'm interested in. I take 9 kids and I give them tutoring. And then I find their mean. My question is the mean of the tutored students significantly different from the general population? In essence, another way of saying that is, do the students constitute a different population? Right? A different population with a mean that is not 40. It's another way of asking the question. All right, so let's formally do that. These are the steps to do. I kind of, I don't always do it in order, but you could. First, we're going to set up our hypotheses. Okay, now I believe I said this the other day, but it bears repeating. The hypotheses we set up are 2 statements. There are 2 statements. I've been talking about the null, but there are 2 hypotheses that we set up. These 2 hypotheses are what we call mutually exclusive and exhaustive. Mutually exclusive and exhaustive. Mutually exclusive means that if one is true, the other can't be true. Like, if you're a registered Republican, you cannot be a registered Democrat. They are mutually exclusive. Okay? The other thing about these 2 statements, these 2 hypotheses, is that they are exhaustive. Exhaustive meaning they exhaust all possibilities. They exhaust all possibilities. So the two statements we set up are going to be mutually exclusive and exhaustive. So let's look at the first one. The first one is the null hypothesis. The null hypothesis is written this way, and H sub 0. 0 for nothing, null. Nada. Okay? Hypotheses are always about population parameters. They're always about parameters. Your question is, essentially, do the tutored students, do they have the same mean as the non-tutored students? So the way you'd write it is the population mean equal to 40? It's not a question. That's the statement. The null hypothesis here is that the population mean is equal to 40, right? Because that's the national average. And again, so you see mu, population mean. I never, ever, ever want to see an X bar in a hypothesis. Hypotheses are always about parameters because your question is about the population. You know what happened in the sample. You know what happens. You want to extrapolate this to the population. Okay? So this is my null hypothesis, right? And by the way, look back at the wording again for the moment. Is the mean of tutored students different from the mean of the population of students who take the AP test who aren't tutored? Is that a directional or a non-directional test? Non-directional. That's why it's set up this way. Okay? If it was directional, we'd wind up having something being greater than or less than. Okay? Now, the second hypothesis that we set up is something H sub 1. Sometimes you might see it written as H sub A. And that's called the alternative hypothesis. The alternative hypothesis. Sometimes it's called the full hypothesis or the research hypothesis. All right? And this is that it's not equal to 40. Because again, remember, null hypothesis testing is an indirect way of getting at your answer. What we're hoping to do is if I reject the null hypothesis, I am left with the other one as the answer. That's why we set them up this way, right? We set them up so that they're mutually exclusive and exhaustive. So if I get rid of one, I'm left with the other one. Yeah, back there first.
So like on the test, would you want us to indicate what mu is referencing? Because in the problem, mu is 40. So if we were to write out, like if you were asking for the hypotheses, would we write like mu of?
You could. You totally could. You totally could. Often I'll ask it in words. I'll say, tell me in words what this means. So, okay, yeah. Right.
So then, does that just mean that when you're tutoring, it's not equal to 40?
Yeah, your question is, are these kids who get tutored, and let's say, do they constitute a separate population whose mean is not 40?
Oh, okay, so that means
Right.
the population of the...
Tutored kids. That's exactly what she was saying. Yeah, no, that was what she was questioning. I generally don't write it that way just because, most books don't. I never learned it that way, but you could. You could write mean of the tutored students. Yeah.
So mu for both setups here, you're talking about the tutored students, not the
Yeah.
mu that we could use comparing it.
Yeah. Yeah. Yeah.
For this example, say like x bar would be 44. Couldn't you say that greater than 40 if you know that the observation you're dealing with is greater?
Again, really you're supposed to set this stuff up before you look at your results. Right? What you're saying is, okay, if this was directional, and by the way, if I'm drawing a directional hypothesis, I usually start with the alternative first because that's more intuitive to me. So let's say I think, before I've looked at my students, okay, I think that tutoring is going to help. So an alternative hypothesis would be greater than 40. And then the null would be less than or equal to 40. All right? But you decide on that beforehand. Why do you decide on that beforehand? Because this determines whether you're going to do a one-tailed or a two-tailed test. Okay? Are we good? All right. Okay, so let's look at the next thing. We're doing a z-test, right? Because that's all we know at this point. Alpha is going to be 0.05. One-tailed or two-tailed? Two-tailed. Now, we could find the rejection regions for that. Let's draw the picture and do that. You could calculate the z first, or you could do this first. I don't really care. I'm on a roll here, so. All right? So we have alpha two-tailed. That means it's going to be 0.025 in each tail. Now again, if I'm going to decide on, if I'm going to make a determination for significance or not, either I'm comparing alpha to what? To make a decision for significance. We haven't gotten there yet, but if I was going to, I compare alpha to what? The p level. Or what else can I compare? My z's, right? My z to my z critical value. We're going to do that. Like I said, we're mostly going to be doing that, so let's get into the habit. So I need to find those z critical values. I'm going to tell you what they are because this is a number you're going to see a lot of. Okay? Plus and minus 1.96. Get used to the number. And again, how did I find that? How do I know that number? I look in the table, beyond z of 0.025, and that's what it's going to be. Okay? So now let us calculate our z-scores. Okay? And by the way, I draw your attention to how you make these decisions. When you do it in SPSS, it's going to be different. SPSS, you're comparing probabilities. Doing it by hand, you're usually comparing z-scores. So just be on the lookout for that. All right, what do I need here? Yeah, let me get my standard error. My standard deviation divided by the square root of n. What's my standard deviation? Yep, what's n? 9, good. So the mean so the z that I obtained, the z that I calculated from my data is 2.40. Everybody see where that came from? Right? That should be clear if nothing else is. Okay. Now I have to make my decision. Where does this z fall on this graph? Well, it falls, let's say, about out here. Okay, a z of 2.4. So here's my first question to you, right? There's a bunch of questions. First question, you have to think for a minute. What is the probability of getting a mean of 44 from a sample of 9 students? 44 or less, actually. Or 44 or more, rather. From a sample of 9 students, right? You cannot give me an exact value based on what I've shown you up here, but you can give me a relative value, bigger than, less than, something. This is real important, so I'm stressing this. The probability, the relative probability of that result. Think about it. Take a risk. What do we think that probability is? Again, you're not going to give me a number. I don't have a number up there for you to see. But you can tell me it's less than something, greater than something. Are you seeing it? Look at where the value falls. Yeah. Well, is it greater than or is it less than? Less than, right? Why less than? Because the z falls out there, right? So it's more extreme than 1.96. So the area under the curve is going to be smaller. Less than. Less than 0.025, yeah. Not greater than. What?
Which side are you talking about?
You tell me, right? If this is the z, okay, this is this z, 2.4, and I said, what is the probability of getting a z of 44 or more? Right? It's going to be here. So is that greater than or less than 0.025? Less than, right? It's a smaller area. This is 0.025. It's a smaller area. Yeah?
So is there another way to say that the area beyond the z-square that you obtained is smaller than the z-square of your alpha?
Yeah, you could say that. Yeah. Or essentially, the shorthand would be the p level would be smaller than alpha. Right? If you looked it up, the p level would be smaller than alpha. But I just want you to get used to this idea of like, oh, right, the probability of getting a 44 is small. How small? Less than 0.025. Actually, hang on to that question just a second. Actually, the way we'd write it is that the probability would be less than 0.05 two-tailed. Once you say that, everybody knows it's divided in half. But it's real important to me that you understand what that means in terms of the likelihood of that result. Yeah?
So being the z-square is higher than the, like when we have the level would be lower.
Yeah, exactly.
So the percentage.
Yeah, the p level, because probability, percentage, whatever you're talking about.
Is that supposed to be 0.025?
In here, that whole area is 0.025. This is also 0.025.
You just wrote 0.05.
No, I said right 0.05 two-tailed.
Oh, so that just
It tells everybody that they know it's divided in half. Everybody writes it that way. Yeah, did you have a question?
When you write it like that,
Yeah.
you're not really telling your audience though, like which side of the graph falls on.
No, just this by itself is not telling you where it's located. What you might do, there's a couple ways you might do it. You might say, well, first of all, let me answer these two questions and go back to that, right? So one question was the probability of that result. Fine, we got that, okay? Do I reject or do I fail to reject? Do I reject or fail to reject the null hypothesis here? I reject, right? So are my results significant or not? Yes. Yes. Okay? So you could, to get back to your question, you could say that tutoring significantly affected the AP results, or you could say it significantly increased them, or would be more typical in a report, you would also be reporting the mean, so they'd know which direction it was. Yes? Okay, so bring it back to the question, folks, right? The question is, do kids who get tutored, are they significantly different from the kids who didn't get tutored? What's your answer? Yeah, they are. They are. Because the probability of getting a 44 under these conditions is so small, how small? Less than alpha, that we say it could not have been due to chance, it must have been due to the tutoring. That's what's going on. That's what's going on. Okay? Yeah?
To answer the question a little bit, we have to do what we just did. You know that the mean of tutoring students would have been different.
We know, again, what's the question? We know that the mean of the tutored kids is different. The question is that difference due to chance, or is it due to the tutoring? So we find out the probability of the result. The probability is really, really, really small. Therefore, we say, I don't think this was due to chance. Because again, what you're trying to do is extrapolate to the population. You know? Okay? All right. I'm just going to mention a couple more things, and we're actually going to end a little early because you have to do evaluations. You have to do fourth week evaluations. By the way, understand something. There is a difference between what we call a true experiment and a quasi-experiment. I think I may have mentioned this before, but let's bring it back again. A true experiment is when I can randomly select the people. Okay? A quasi-experiment is you have a pre-existing group. So the AP kids, that's a true experiment because I randomly selected kids to tutor, in theory. The power line kids, also in theory, they were randomly selected. But let's say you were studying anxiety in a group of people or something. You take a group of anxious people. That's a quasi-experiment because that's a pre-existing group. The analysis is the same, but the generalizations of your results are different. You have to be much more careful if you have a quasi-experiment. Okay? Now, in every experiment that we do, there are going to be assumptions that we have to meet in order for the results to be valid, really. Okay? One, the sample was drawn randomly. We spoke about that. And independent, right? That selection of one person is not affecting the selection of another person. It doesn't change the probabilities. The second one, the variable measured has a normal distribution in the population. If it doesn't, what saves us? The central limit theorem. The central limit theorem. Okay? And that the standard deviation for the sample population is the same as that for the comparison population. In this case, that might have been true. I didn't give you that data. Very often in new research, we don't know that stuff. We don't know that stuff. But, that's an assumption that we're talking about. Now, we don't perform one-sample tests very often. I show you this because it's the underpinning of all the other tests we're going to do. We almost never do them, though, because there's two major problems. One is that the results of this test are heavily based on random selection. So if you don't have it, it really is a problem. Okay? That's one problem. The other problem, and I don't know if you can see it, but if I'm making a comparison between kids who live near power stations and their intelligence, what am I missing? What am I missing in that? Can you think of what I might be missing to compare them to? How about a control group? A control group, right? You don't know if those kids were smart because they live near power stations or because of a variety of different things, because I have no control group. I have no control group. Okay? All right, so we're going to stop here.